Thanks for attending our webinar about choosing the right charge controller. This is a joint webinar presented by Morningstar and Unbound Solar. Unbound Solar is one of Morningstar's distributors, and we've been partners for many years. Before we start, let me remind all attendees that you can type any questions into the question chat box at the bottom of your GoToWebinar pane, and we will address them at the end of the webinar or via email if we can't get to all of them. We're going to be recording this broadcast and emailing you a link to the recording before the end of day tomorrow. And we've also included a copy of this slide deck in the handout section of your GoToWebinar pane that you can go ahead and download right now. All right, with that said, let's go ahead and introduce today's speakers. My name is Mark McHenry. I'm a marketing manager with Morningstar, and I'll be moderating and sharing some brief information about Morningstar before I hand off to Josh Roelofs of Unbound Solar. Josh will share some information about Unbound Solar and present what you need to know to choose the right solar charge controller for your application. So let me start by sharing a little information about Morningstar. We can go ahead and advance to the next slide. There you see Morningstar is a U.S. company that conducts business through authorized distributors and dealers all over the world. Since 1993, we've been a leading supplier of solar charge controllers and inverters with the same ownership, same management and distribution partners throughout our history. We pride ourselves on our product quality, reliability, and innovation, and we've been dubbed the charging experts. You can see that over 4 million Morningstar products have been supplied worldwide since our founding, and we have the lowest published hardware failure rate in the industry. And when trade shows start up again, we'll be exhibiting at Solar Power International, Intersolar Europe, and many other solar shows and conferences in Europe, Africa, Asia, Australia, and North and South America. All right, so with that said, Josh, please tell us a little bit about Unbound Solar and what people need to know to choose the right solar charge controller.
Thanks, Mark, and thanks to everyone at Morningstar for helping organize this. I'm Josh Roelofs, tech support specialist from Unbound Solar. I've worked here for over 8 years doing sales, design, product management, technical support, and services. Unbound Solar is a supplier of solar solutions, including kits and components. We offer system design service, and we do electrical design drawings. We're serving residential, commercial, industrial customers for pretty much any application related to solar and storage, off-grid, grid-tied, hybrid, grid-tied with storage, battery backup. We've been a leader in DIY solar. We were formerly called Wholesale Solar, and more than 20,000 PV systems designed and shipped. Come check us out at unboundsolar.com. All right, let's talk about charge controllers. Why is it important to choose the right one? Number one on the list is just it needs to be compatible. It needs to work with the other system components, your PV array, your batteries, anything else that's in the system. Number two, we need to charge the batteries properly. And this is the requirements are going to depend on your battery type. Lead acid is the most common. Lithium ion has also grown in popularity. Some controllers are only built or designed for lead acid. So unless those charge set points or profiles are adjustable, you might not be able to do lithium ion on every controller. You might not be able to charge those batteries. And of course, even with lead acid, there's different charge profiles or set points that we want to make sure we can accommodate. The third on the list is just to minimize risk of system failure and downtime. This is pretty obvious, especially if the site is in a remote location or if replacing components is difficult or expensive. And then number four, we want to optimize the PV charging efficiency and wire size. By selecting the right component, the right controller, you can make sure that you're not buying oversized wire or needlessly buying large wire when we could use a different controller and a different design to better optimize that. So that's why it's important. Here are the steps we're going to cover in choosing a charge controller. There's two types of charge controllers. We need to pick between maximum power point tracking, or MPPT, and pulse width modulation, or PWM. So we'll cover a little bit about the applications and when you would choose one over the other. We're going to talk about other features and requirements when looking at a charge controller that you need to consider. We'll go over some system sizing examples for both controller types. There are also some related parts, some circuit breakers, some accessories. Some of these are necessary for code and safety, some of them optional accessories or maybe needed depending on your application requirements. So we'll try to touch base a little bit on that. And of course, time for Q&A at the end. Let's talk a little bit about the two controller types. And if you really want to learn more about this, spend some more time on it, Morningstar is a white paper, which I've linked at the bottom of the slide, and you can also find on their website, of course. So that's a good resource, but here's the basic summary. An MPPT controller is going to be used typically for larger solar arrays. It's going to offer much higher charging conversion efficiency, usually 15, 20, if not 25% more efficient than a comparable PWM controller. So pretty big efficiency difference. The thing that really distinguishes an MPPT controller is the high input voltage from solar. What you have is a relatively higher, oops, sorry about that, cat stepped on the keyboard. You have a higher voltage coming in from solar that gets converted to a lower voltage for charging batteries. An MPPT controller is going to lower the incoming voltage and raise the current proportionally at a very high efficiency, about 99% efficient. And so essentially we're coming in with a higher voltage and than what we would typically see at the battery charge. This higher voltage is really beneficial for long distances. If you're going certainly anything over 50 feet from PV array to the batteries, you'd probably be looking at an MPPT. And when you get up to several hundred feet, let's say more than about 200 feet, or that'd be about 60 meters, that's when you'd start looking at a high voltage MPPT, such as a 600 volt controller that's really going to optimize that power transmission for longer distances. A PWM controller, typically smaller solar arrays. Usually if you're just doing 1 or 2 solar panels, we'd be using a PWM controller. Like I said, the efficiency quite a bit lower, but they are still a cost-effective option. The big thing that distinguishes a PWM controller, and I have this underlined, we have matching PV and battery voltage. So the voltage of the PV panels and the voltage of the battery bank, they have to be the same. You can't come in with higher voltage like an MPPT. So we're losing that benefit of being able to use high voltage for longer distances and for smaller wire sizes, but they are still cost effective. Usually smaller systems, it doesn't mean you couldn't build a huge array with a PWM controller. It ends up just being, it has some limitations, and at a certain point it actually becomes more expensive to go that route. Some other things to consider when you're looking at a controller. Number one, usually the first thing I look at is how is that controller cooled? Is it actively cooled with fans, or is it passively cooled with a heat sink? You can see the TriStar MPPT 600 volts, that upper left image on the screen, large black heat sink on top. All Morningstar products are passively cooled. Depending on the brand that you're looking at, this does vary a little bit, and especially when you get into the higher power, the 60 to 100 amp MPPTs out there, most of those are cooled with fans. That has a couple of drawbacks, excuse me. A big one is that you're pulling anything in the room, whether it's dust or other debris that can kind of get pulled in, you're potentially blowing that across the circuit board, shortening life of components. It's also another part that can wear out, the fans, and then they have a parasitic self-draw. We're powering a fan that we wouldn't normally have to do, so that has some self-loss, which kind of leads into the second point, the efficiency and self-consumption. Most modern MPPT controllers are going to be very high efficiency, probably 98 to 99%. Self-consumption should be, low. Usually it can depend on if you have a meter or something, but it's often a watt or less. But these are some of the things that you might compare at the initial stages if you're looking at different brands or different controllers. Number three can be a big one depending on your requirements. You want to consider the monitoring and communication that you need. If you need to remotely access data, log data, receive fault alerts, some of the bigger controllers are going to have Ethernet connectivity built in, like the TriStar 60 amp, the TriStar MPPT 60 amp controllers will have an Ethernet port. Some of the smaller controllers, they're going to have an RJ11 phone cable, and you have to use that EMC1 adapter. And then the really small controllers like the Sun Savers, they actually don't have any communication capabilities, which is okay in a lot of small setups. So it's just something to consider at this stage. Number 4 on this list is the ability to control a relay, or related to this is automatic generator start. Morningstar uses a relay driver accessory to be able to accomplish this. Sometimes you can find, if there's an inverter in the system, your inverter might be able to control a relay, or there might be a separate dedicated auto gen start module from the inverter company. So it's not that you necessarily need this on every system with a generator. It's just something to consider when you're picking a component. A lot of residential systems, they'll have an inverter that actually controls their auto gen start. So not necessarily a requirement, but something to consider. Number 5 is lighting and load control. Some of these controllers are going to have terminals for a DC load, a 12 volt, 24 volt load, for example, and the ability to intelligently control those, like lighting controls based on daylight hours, or other load controls, timers and such. So if that's something you need, maybe lighting would be the most common application, but any other DC loads, if you need the ability to control those, you'd want to look at a controller that has those load terminals, something like the ProStar, Sunlight. The Sun Savers have load terminals, but no load control. ProStar and PPT. On the other hand, if you don't have DC loads, you won't even consider that, so it may not be an issue. The TriStar controllers don't have that set of load terminals. So that would be ideal if you didn't have DC loads, or you had a separate means of controlling those loads. The 6th thing I have on the list here is just certificates and other standards that may be required depending on your area and application. I listed out some common ones. This is by no means everyone that applies, and not all of these are required in every area. Some of these are specific to certain areas or applications. You mainly just want to make sure your controller that you're installing is going to meet the standards and requirements. So if this is getting, for example, if this system's getting permitted and it's subject to National Electric Code, that's going to be a different set of requirements where you're looking at things like arc fault protection and ground fault protection, versus something that's a remote site might not be subject to all those same requirements, but you still want some basic, CE compliance, maybe a UL listing just for good measure. One note on here is that if you're running into anything in the market, if you find yourself, your customers need a certain certificate or a certain feature, a certain standard, please share that feedback with us here at Unbound Solar and with the folks at Morningstar. We really invite feedback from our customers to make sure that they're getting everything they need, and that we're essentially staying on top of the latest trends and codes. So if there's something you need in a controller that you're continually coming up against, maybe you're finding all of a sudden you have to add the ground fault protection device on all these systems, send us that feedback, and we can definitely try to consider that and account for that as we're designing and selling these products. Those are the main things I look at beyond just, is this, what is kind of the credibility and the reputation of the company? Obviously for any product, and especially critical power electronics, we want to make sure we're working with companies that have some track record, reputation, and just try to find good reviews if it's not a company you're familiar with. There's only a handful of established charge controller manufacturers in the US, so it's not like there's a huge array to choose from, but these are kind of what I would look at after making sure it's a reputable manufacturer. Charge controllers can be used for a number of different applications, ranging from industrial, commercial, to residential, leisure. In some of these systems, the cost of replacing or fixing a controller can be extremely high. It might involve a helicopter site visit, a snowmobile out to a remote location in the mountains, or even your remote cabin that is seasonal and isn't accessed all year. So that's why it's really key to get a controller that is first of all designed and sized right, and also is going to hold up over the life of a system. In a lot of cases, replacing your controller can be a lot more expensive than the controller itself, which isn't necessarily a huge amount. When you're searching for a controller, it's got a few bullet points here. Obviously, we're looking at performance, logistics, being able to get it, the certifications, some of which I covered on the last slide, and then features. And this is not an exhaustive list. There may be, depending on your requirements, some specific features that I haven't covered here. All right, next we're going to cover system sizing using a PWM controller. We're starting with PWM because it's a little bit simpler than MPPT, and I'm hoping this is fairly straightforward if it's not something you're already familiar with. The first thing we need to do is make sure that the charge controller current is greater than the solar panel current. That probably sounds pretty obvious, but we're going to look at the spec sheet and we're going to use short circuit current, which is denoted as ISC on the solar panel spec sheets. So the 100-watt panel I looked at had a short circuit current of 5.94 amps. Simply put, we need a charge controller that can handle at least 5.94 amps. I rounded up to the next size, a 6 amp controller. This is fairly straightforward. Morningstar and most controllers, you can even overload them a little bit. You'll want to check the data sheet, of course, and confirm with the manufacturer. For some manufacturers, you may even be able to use a 5 amp charge controller. Honestly, this is a pretty small configuration and there aren't a lot of charge controllers available under 10 amps. So first step, making sure the charge controller current is greater than the PV current. I think that's pretty intuitive. Second, we need to match the battery and the PV nominal voltage. The big distinguishing thing with PWM is that the solar voltage has to match the battery voltage. So I have a table here. The left column, we have solar panel types. They're denoted by the number of cells, 36, 72, 60, 96 cell. These are the four most common ones. There's common panel sizes in that second column. The voltages, open circuit and max power voltage, those are approximate. That's going to vary depending on the wattage. And then the nominal battery voltage that the panel corresponds to. So I'll quick run through this first row with 36 cell panels. These are typically about 5 watts up to 180 watts, open circuit voltage of around 22 volts, and a max power voltage of about 19. This is a 12 volt nominal panel, so one of those would correspond to a 12 volt PWM controller and a 12 volt battery bank. Of course, the actual voltage is about 19 to 22, maybe a little more or less depending on your exact panel, but it should be about within a volt of those ranges. So a 36 panel is a nominal 12 volt panel. The next row, 72 cell panel, is essentially the same thing but doubled. That's a nominal 24 volt panel. These are the only two sizes that were really designed to work with a PWM controller. The voltages for those panels were designed specifically to charge batteries through a PWM controller, so there's no issues. There's no issues there as long as we pick the corresponding panel and battery voltage. It's going to work, and it's pretty simple. 60 cell and 96 cell panels were not designed to work with PWM controllers. And depending on your exact location and your panel specs, there's a couple of issues that could come up. Even though some people have maybe done this with a 60 cell panel, there are some drawbacks and some limitations. And I'll try to quick show you what the issue is. If you look at the max power voltage on a 60 cell panel, it's a little over 30 volts. It's about 31 volts, a little bit higher now that they're creeping up in power. If you're trying to charge a 24 volt battery at that voltage, depending on the battery type, your 24 volt battery needs to charge at about 28 to 30 volts. If it's a flooded battery, you might need to equalize that at about 32 volts. So already we have about 31, 32 volts coming in from solar, and that's before we lose anything to heat or voltage drop. So potentially only 30 volts coming in through solar. 30 volts is not enough to charge a flooded lead acid, unless it's, if it's cold, you might be okay. If it's a sealed lead acid and you don't equalize, you might be okay. If it's a lithium battery and they charge a little bit lower, you'd probably be okay, or maybe a higher voltage panel. But that's sort of where the issue comes in, is that you have a panel that produces just over 30 volts and you're trying to charge at that same range. So if there's any loss from a temperature, voltage drop, or other factors that can affect system performance, your voltage won't be high enough to charge. So the 60 cell panels and 96 cell panels were not designed to work with PWM controllers. And generally we would recommend an MPPT controller if those were the panels you were using. 60 cell panels are quite common. 96 cell panels are not very common. Panasonic and SunPower are the main manufacturers. You don't really see those much. One note is that if you are working with SunPower panels, the 96 cell SunPower panels are positively grounded, so your charge controller would have to be configured for positive ground, but that's not something we see too commonly. So hopefully that gives you an idea of how these different solar panel sizes, and it's really the two sizes we're concerned about, how they match up with the nominal battery voltage. A 36 cell panel is a 12 volt panel, a 72 cell panel is a 24 volt panel. Let's look at a few examples. On the left, I have left side, I have specs for a couple of solar panels, a 100 watt panel, which is a 12 volt panel, and a 365 watt, 24 volt panel. And then on the right, I have a table with a couple of example systems. I'm not going to go through all of these. We'll send you a copy of this later you can use for reference, or feel free to take a screenshot if it helps. But basically, these are just example configurations. The first one is 100 watt panel, 12 volt battery, and then a recommended controller, the SunSaver 6 amp. This just shows you how wiring in series and parallel is going to affect the voltage and current, and how you can pick a corresponding controller that that meets the need. You know, again, we're just matching the panel and battery voltage, and then we're making sure that the controller can handle enough current. And keep in mind, of course, our series parallel wiring in series is going to increase your voltage, and wiring in parallel is going to increase the current or amps in the system. I won't spend too much time going over this table. Oh, one note, for a 48 volt system, we had to go up to a TriStar controller because they can do a 48 volt battery bank, where some of the smaller ones like the ProStar does 1224, the SunSaver is only available in 1224. So we had to move up to a TriStar controller for 48 volts, even though it wasn't a high current requirement where we really needed the 45 amp controller. All right, next we'll cover the steps for sizing an MPPT controller. And there's basically three key things we're trying to look at here: the max input watts your controller can handle, the max volts, and then the minimum volts that we need from the PV array. Starting with number one, max input watts. You can calculate this by multiplying the controller amps times the battery voltage, and this will give you an approximate max solar watts. In Morningstar's case, they have this on their data sheet, so all you have to do is look at their data sheet, and it also has a note that you can actually overload the controller, and it's going to limit to these values. So you can actually put in a larger solar array, and it's obviously going to limit the current output. One note about this, it kind of helps demonstrate why you would move up to a higher voltage for a bigger system requirement. Sometimes customers will ask us, you know, when should I move up to a 24 volt system instead of 12 volt, or when should I use 48 instead of 24? When is it beneficial? And I think this does a pretty good job of showing why it's so beneficial to move up to 24 or 48 volts for higher power requirement. The simple answer is that same controller can handle 2 to 4 times the watts of solar just by moving up in battery voltage. And there's some other improvements too with just the inverter efficiency and wire size. But this is mainly the reason why we move up to 24 or 48 volts. As the power requirements get bigger, is we're just lowering the current on that controller, and the same controller can utilize a lot more current. I think this is pretty self-explanatory. You know, there's a wattage limit. If you do overload it, in the case with Morningstar, it's just going to essentially limit off the excess wattage, so you're not harming anything. You do want to check with the manufacturer before, you know, before oversizing an array like that, because some manufacturers will have limitations. But in the case of Morningstar, it's going to be able to handle an overload and just limit that output. The second thing we're going to look at is the max PV volts, which is really key because we can't exceed this at under any circumstances, or it'll damage the controller. In this case, the TriStar MPPT controllers are rated for 150 volts. There's another set of TriStar controllers that's rated for 600 volts, which is what we'd use if you had really long wire runs or long distance from your PV array to the battery. So we need to design a system that will never go over this 150 volts DC. If you exceed that in any condition, and it could be caused by cold temps, it's probably going to damage the controller, and it's not something that would be covered under warranty. So it's really key that we never go over voltage. And the third point that's related is there's a minimum volts to be able to charge. You know, if we're going to charge a 48 volt battery bank, we can't come in at 20 volts. The controller can't raise that incoming voltage, it can only lower it. So we have to have a high enough voltage from PV to charge at the highest charging voltage at any temperature, and then I usually recommend 20% headroom there. Let's go over a quick string sizing example. And this will show you how you can calculate max voltage from a solar panel. I have a solar panel spec sheet here. This is probably a lot of information, so I tried to highlight a couple of things in red rectangles. We have the solar panel power specs, the watts, volts, amps, and then we have a temperature coefficient highlighted towards the middle. And then towards the bottom, I circled the cell temperature of 25 degrees C, which is what all this is based off of. So what does all that mean? This solar panel, it's a 365 watt Astronergy panel in this case. It's going to produce 39.8 volts max power, 47.82 volts open circuit, and then about just under 10 amps, depending on the current rating we're looking at. What we need to do is account for the effects of temperature on voltage. And that's why I highlighted that temperature coefficient for VOC. What that says is that for every increase in 1 degree Celsius, you lose 0.282% of your volts open circuit. And the opposite happens when it gets cold. If the temperature goes down, your voltage goes up. I think it's kind of intuitive if you think of it as the hotter it is, the less efficient your system works. And then the colder it is, it actually gets more efficient and you can produce a little bit more than the rated value. What we want to do is make sure that this panel is not going to go over voltage and exceed the limits of our charge controller, because that would damage it. So if I look at an example using 0 degrees Celsius, which is freezing, that's a 25 degree change in temperature from the cell temperature and the specs. So 25 degrees times 0.282%, it's just over 7% change in voltage. That's simply how you could calculate that voltage change depending on a given change in temperature. So our voltage is going to be just over 7% higher at 0 degrees Celsius. In this case, that actually pushes the panel a little bit over 51 volts, 51.19 volts for each panel. So 2 in series, you're 102 volts. 3 in series, you could actually exceed 150 volts. So this just shows us that at 0 degrees Celsius, this panel is going to open circuit at 51.19 volts after we correct for temperature. So if we're using that 150 volt controller we were looking at in the last slide, the TriStar MPPT 150 volt, we would actually be limited to 2 in series in this case, unless it was a warmer climate and we could change that calc so it's no longer going over 150. But at least based on this example, which is kind of a worst case scenario, it would actually go over 150 volts. We would want to stick with 2 in series. Now you could use 2 in series for 12, 24, 48 volts. It would be high enough. If we look at the VMP, it's still going to be more than enough to charge the batteries, more than high enough to charge any 48 volt battery bank, but still not high enough that it's going to go over voltage. So in this case, we'd either have to do 2 in series, or we'd be looking at the 600 volt controller, which would typically be used for a really long wire run. There are some related parts that are going to go with the charge controller. Overcurrent protection is something that's necessary for safety and usually for code too, and it's not included in the controllers, either fuses or breakers, and I'll show a diagram on the next slide of that. You're also going to need a PV combiner or splices in most cases, unless it's a very small system. We recommend Midnight has a full line of MNPV combiners in really any size and configuration you want. If it's more than 2 strings, you need a combiner with a fuse or breaker on each string. If it's just 2 strings, you can use an MC4 branch coupler, which is just a plug and play. Assuming the panel has MC4 connectors, it's just a plug and play way to combine 2 strings. And then of course, wire and cable to connect the PV panels into the combiner, and then from combiner back to controller. And of course, make sure you're sizing for voltage drop, assuming it's more than 20 feet. You'll probably want to bring up a voltage drop calculator and make sure that it's not excessive. We'd usually recommend aiming for under 3% voltage drop on that DC circuit from the panels to the charge controller. That might vary a little bit just depending on your system and requirements, but usually we'd shoot for less than 3% voltage drop on that run. Here's a diagram showing the 2 necessary circuit breakers or fuses required for every charge controller. If you had a load, like a 12-volt load hooked up to this, you'd need a 3rd fuse or breaker for that on the positive wire, similar to these. So the one on the left is your input breaker or your solar disconnect. It's simply between the solar array and your charge controller input. This will allow you to shut off your array when you're servicing or doing maintenance or replacing a controller, and then it also protects it from overcurrent. You'd want to size this based on the size of the wire. And essentially the breaker's protecting the wire, so they need to be rated for the same current, or the breaker could be smaller than the wire's rating. So if that's number 10 wire, if it's number 10 PV wire coming in and it's rated for 30 amps, you would simply use a 30 amp solar input breaker or a fuse, but in most cases we'd recommend a breaker unless it's a very small system. On the right, it's showing the battery breaker or battery fuse. Typically the manual will tell you what size breaker or fuse to use here. If it doesn't, I would take the controller continuous output, let's say that's a 40 amp ProStar, and multiply that by 1.25. So if that's a 40 amp ProStar controller, I'd multiply 40 amps times 1.25 and use a 50 amp output breaker. And again, you need to make sure that your wire would have to be rated for at least 50 amps in that case. So making sure that your breaker, your overcurrent protection is protecting the wire. So in summary, you choose a controller based on the application and power requirements. MPPTs are usually bigger power requirements. PWM is typically 1 or 2 panel smaller requirements. Consider any other essential design requirements and features, things like, is it active or passively cooled? Do you need to communicate with it? Certifications, and just anything else that might be required. Size a controller based on the PV array size, using the processes depending on if it's PWM or MPPT that we showed previously, and then add any breakers or other necessary balance of system components. This photo here is a remote industrial site that was, at least at the time when they installed it, it was only accessed by helicopter or snowcat in the winter months. So you can see getting the right controller and making sure it's sized right and is going to hold up and last. If it's an application like this, it's really critical. And also, even if it's your residential, your cabin, your off-grid home, or an RV marine application, it's really just as important, because you never know when it might go out and what it takes to get a replacement. So that's why you really want to consider this process. Of course, we don't expect you to memorize all of this, and we're here to help. So if there's anything we can do to help you with system design, component selection, the folks at Unbound Solar and Morningstar are here to have your back. And with that, I'm going to go ahead and open it up to questions from the audience.
Okay, terrific, Josh. Thanks for that presentation. Hopefully you can hear me. I'm off mute now, and I'm going to take a look at what questions came in. Actually, we had somebody emailed me a question the other day when they signed up for this webinar. The question is, how can we minimize the creation of dirty electricity by choosing the proper controller and doing anything in terms of shielding or twisting wires? So you want to go ahead and try to answer that as best you can, Josh?
Thanks, Mark. Yeah, that's a good question. Any power electronics, or really any part of the power electronic system, including the wire, is going to produce electromagnetic interference. And so there's a couple of things we can do to minimize that and help mitigate it. And this can be an issue if it's a telecom site and you have communication equipment that's sensitive. This can be a real concern, especially if it's in close proximity to your equipment. So there's some best practices in the installation you'll want to adhere to. Keeping the positive and negative wires close together is good practice, ideally zip tied together. You may be able to twist them together if it's a very small application and a very small controller and PV array, but usually you're kind of stuck putting them in the same conduit or zip tying the positive and negative wires together. That helps reduce the magnetic field created by the power flow. Uh, Putting your controller as close as possible to the batteries and minimizing that length from controller to batteries is going to be good practice as well. If it's an MPPT controller, that's going to be the highest current in the system, so we definitely want to minimize that length. The TriStar PWM controllers have an on-off mode that can be used as a last resort. So if you find that you've tried these other measures, you've separated the equipment as far as possible, and you have your controllers interfering with your equipment or causing some other issue with interference, there is an on-off mode that you can use, which basically dumbs down the charger. This is not really ideal. It's sort of a last resort option. The reason being it's not going to charge your batteries as effectively, so you might have impacts with things like just charge efficiency and battery longevity if you're using on-off charging. But if you have a site, you're having issues with noise and it's the only thing you can do, the regular TriStar PWM controllers can be switched to an on-off mode. Another thing that's used is ferrite beads or ferrite chokes on the wires, but as far as selecting those and where they go is probably beyond the scope of what we can cover here, but hopefully that helps.
Okay, very good. Thanks for that question and thanks for the answer. I see another question that came in from Lauren. Lauren says, my inverter won't operate my washer and dryer. Any ideas, why it won't work and what will work to do that? So maybe this is kind of it could be a lot of different reasons for this, but any quick suggestions as to what Lauren can do to
Yeah,
operate the washer dryer?
that's a good question, and I bet the issue, at least the most common issue that comes up in terms of inverters and washer dryers, is related to particularly newer appliances don't have enough power factor correction built in. Or I guess you could blame it on the appliance company, or you could blame it on the inverter company and say, some of these don't have enough power factor correction built in, and that's what seems to be causing these issues, at least in our experience. There are some write-ups where folks will actually add a run capacitor into their appliance. It's usually a small separate box you'd wire it into, but basically the addition of a small inexpensive capacitor in the right part of the circuit fixes that issue with it not having enough power factor correction. And we have seen this come up with a few inverters. It seems like some brands are maybe worse than others. Lauren, I definitely encourage you to reach out to whoever sold you or installed that system. See if they can have any insight into other customers and if they have any experience with that. If this is something that you bought from Unbound or Wholesale Solar, start a tech support ticket, and we'd be able to help you look into this and provide further explanation. Beyond that, I can try to look on my own and see if I can find some of the explanations I found. But essentially, I think the issue is that either the appliance or the inverter doesn't have enough ability to correct for power factor, and that's why some of these new washer and dryers aren't working on the inverters, even though other appliances may work and it may work fine on a generator.
Okay, very good. I see a question that came in here about 72 cell and 60 cell modules. Are you able to backtrack to that slide, Josh? It was probably about like 5 slides ago or so. Yeah, I think that's it. Actually, 3 slides ago. Okay, so let me see. They were just, I think there might have been some confusion here. So they're trying to clarify. They said they're saying the 72 cell module has higher voltage than the 60 cell, but they thought that the arrangement of this chart, they were a little bit confused, and they thought maybe that we were trying to say, oh wait, oh, okay, I see. No, okay, this is where it is. Yeah, I'm just comparing the 72 cell module. You can see the open circuit voltage 48 or about 48, max power voltage about 38, as opposed to the 60 cell, which has open circuit 39 versus 31. So yeah, all the numbers here look to be right, that the 72 cell has higher voltage uh,
Yeah,
voltages
and I
than the
guess
60 cell.
yeah, and that's it's a good point. It almost seems as though the 24 volt panel, the nominal panel, I mean, it runs at about 48 volts. It seems counterintuitive that a 24 volt panel would work at 38 to 48 volts. Um, think a little bit about how the panel is going to work in the real world. Is that the open circuit voltage is only going to be experienced in the morning when the system is starting up. And then once the charger actually starts, that voltage drops down to max power. So when your system's actually charging, we're using max power voltage numbers. The only thing we use open circuit voltage numbers is really to make sure we don't go over voltage. We use that in design to make sure we're not going over voltage, but the panel's not really doing work at open circuit. So that's why we use the VMP if you're thinking about what does this panel produce when it's charging. So a 72 cell panel, when it's actually charging, it's going to be about 38 volts plus or minus a few, depending on the wattage. This is actually the optimal voltage for charging a 24 volt battery through a PWM controller because there's going to be some losses, and we need that to charge at a minimum of about 32 volts. Keep in mind a 24 volt battery bank, the charging voltage could be as high as 32 volts or maybe a little bit higher, depending on the battery, if it's flooded and if they're equalizing. So yeah, so basically if we're going to charge at 32 volts, the 60 cell panel isn't going to be high enough. And especially as soon as you have heat lowers your voltage. If you have voltage drop, that could be 1 or 2% right there easily. So the 60 cell panel in most cases would not be high enough voltage to charge a 24 volt battery. And that's why we have to go to the 72 cell. Hopefully that helps address the question or at least shed some light on the panel types.
Yep, I think that clears things up. Thank you very much. Let's see, a question here from Alfredo. It says, tropical weather and climate are usually not the ideal environment for solar energy settings. Do you have any recommendations for implementing a solar energy system in this type of climate, tropical weather?
Yeah, obviously, and I didn't really cover this when we were looking at the features you need to evaluate, but in your case, I would definitely spend some time looking at the temperature and humidity range for a controller, and also the derating, the power derating. As temperatures increase, the controllers are going to derate, essentially, and so you would need to look at those derating charts in the manual to be able to figure out, okay, if, depending on the temperatures where you're at, it might be 100 degrees Fahrenheit and high humidity. What is the charger really going to be doing? It might derate by 20% or something like that. So the first thing I would do is just look at the temperature ranges and make sure that it's in a reasonable range. There's also looking at the protection rating of different controllers. So if you're comparing different brands or different models, there is going to be an IP and ingress protection rating that gives you an idea of how sealed or protected it is from the environment. Some charge controllers are simply a circuit board in a plastic box. Some of them are going to be epoxy encapsulated. So there are some differences there. Obviously, in a tropical place, you'd be looking for anything that just has the highest temp ranges, the highest IP rating, the best ingress protection rating you can get, so it's sealed the best. You may also want to look at putting it in another enclosure to protect it. I've heard of issues where things like geckos will crawl across your, bus bars and cause a short. So it could be issues beyond just the heat and humidity that are actually affecting the system here. So you could look at installing it in another box that's going to protect it. However, that further causes an issue where you have temperature rise within the enclosure itself because we're producing heat in a small box. Then Morningstar does have a white paper on how you can calculate temperature rise, and it's pretty simple, and you can use that for any controller inverter. So there is a white paper on how you can kind of calculate that. I guess those would be the main considerations if it's tropical, is just making sure the temperature range is within what you'll experience. The derating is something you can handle. You might have to oversize your system because the charger is getting derated. And then looking at things like ingress protection ratings and just making sure it's as sealed as possible from the environment. Oh, and in terms of humidity, there are some products to help reduce the humidity. You know, there are some agents or products that essentially pull humidity out of the air that you could put in the room or in the enclosure. So if it's really a humid environment, that might be something. And if you have issues with power electronics, that might be something to look into if it's a relatively small cost or low effort thing to do.
Okay, very good. Very good. I have a question coming in from Edgar. Let's see. How can I customize my charge process in a TriStar MPPT controller for different battery technologies? Do I need any additional equipment to do this, to change custom settings, charge settings?
Yeah, you would need the remote control for the meter face. The TriStar by itself has dip switches for basic charge profiles, but it just covers lead acid charge profiles. And even in a lot of cases for lead acid, you'll want to go in and program in custom set points. So you'd either have to do that on the meter or by hooking a computer up to the unit. Of course, correct me if I'm wrong on anything, Mark.
I think that's a good point you made. One thing I should probably just add to that is correct. You can hook up your TriStar MPPT to a computer, and we do have free MS View software. So, for example, if you went to our website, went under hit products, there is over to the bottom right, there's a icon for MS View, and you can download that software. And once you do that, if you hook up your controller to a computer, your TriStar MPPT, you can change its custom settings according to what the particular battery manufacturer recommends. As a matter of fact, if you're using lithium, for example, if you go into the resources tab, we have an energy storage partner program section on our website. So that's resources, hit that drop down, look under energy storage partners, and we've done a lot of this work for you already. So you can click an implementation guide for many different lithium iron phosphate battery brands if that's what you're looking at. But as Josh said, whether it's lead acid or lithium, we do have resources. And if we don't, you can always contact your battery manufacturer. They can give you the proper settings, and with MS View and software and hooking up to a computer, um, you can adjust those settings. Or if you're using for example, a ProStar MPPT, which has an interactive meter interface, you can use the scroll keys on that controller to adjust your charge control settings. So great question. Great question.
Thanks.
All right, let's see what else we got here. All right, so that was from Edgar. Now we have one from Charles. Charles asks, can charge controllers be wired in series on a 12-volt system if wiring the solar panels in series to accept higher voltages for transmission instead of parallel current driven wiring, and then step down the charge to 12 volts? So that's a mouthful. And I don't know whether you're able to see that question, Josh, or should I read that to you again, or is this something you want to take offline? What's the best way to handle this
Yeah,
one?
I think I can try to, if you could repeat it one more time, it would help.
Sure. Yep. Okay. So Charles asks, can charge controllers be wired in series on a 12-volt system if wiring the solar panels in series to accept higher voltages for transmission instead of parallel current-driven wiring, then step down the charge to 12 volts?
Yeah, that's a great question, Charles. So what you would want to use in that case is an MPPT charge controller, and you would not be able to use a PWM controller, or at least you would not be able to carry the power in at a higher voltage. And let's say this is a 12-volt system. You could use a TriStar MPPT or ProStar MPPT, which goes up to 150-volt DC. This would probably be good, assuming your distance from array to battery is less than 100 feet. I think the 150-volt limit MPPT would be good to go. If it's more than about 100 feet, or certainly more than 200 feet from PV array to batteries, that's when you would look at a 600-volt TriStar controller. And so you could come in that case, you could come in at nearly 600 volts. It'd probably be more like 450 volts in the real world, and making sure we don't go over voltage. You could have a PV array coming in at 400 volts, and then it gets lowered to charge a 12-volt battery. That's obviously a really efficient way to carry power over long distances. So I think based on what you're describing, Charles, you'd want to look at an MPPT controller, and then you would want to play around a little bit just with the voltage drop calculator to see, what size wire do you need and how big is it. At a certain point, you'll notice that for really long distances and higher power requirements, the wire size just gets huge. You're using like 2-aught or 4-aught wire for hundreds of feet, and that's when it makes sense to go up to the 600-volt controller.
Okay, thanks for that question. Thanks for the answer. All right, I see a question from Jim. Let's see, is a CKT design available to clip a cold weather high voltage condition to prevent a controller from shutting down?
I'm not sure what CKT, I'm not sure what that
I'm not either. It's a
abbreviation stands for, but
small
it
letter
basically,
CKT period. Yeah, okay.
yeah, and I think basically what you're trying to do in the design is design a system that's never going to go over voltage at the extreme low temperature. And sometimes it's a little bit difficult to know how cold it's going to get in an area. Sometimes that data can be hard to get if you just don't have climate data. You're not looking at the average low, you're looking at the extreme low. How cold is it going to get as a worst case? And then essentially you'd want to design a system that's never going to go over voltage at that extreme low. There are common system designs like 360 cell panels in series on a 150-volt controller. That's not going to go over voltage until it's like negative 100, so nowhere on this planet. So there are some common designs that'll work anywhere. A lot of the packages we sell are sort of in that range where they can basically work anywhere. But basically what you're trying to do is design so that it never goes over voltage. These controllers, the TriStars, do not have over voltage protection, so anything over that would damage it. Some charge controllers on the market, some MPPTs, do have a form of over voltage protection where they basically shut down and go into a safe high voltage mode. And there's obviously a limit on that. It might be, maybe it's an extra 20 volts, or it's the nominal battery voltage 48 volts over. You still kind of want to avoid going over voltage, even if it has that protection feature, because your charge controller is not going to produce power when it goes into that mode. If it has that mode, it's going to shut down, and that's obviously a waste and something to avoid. So in short, we're just trying to design so it never goes over the voltage limit.
Okay, very good. All right, I see a question from Chuck. He says, I am changing from sealed lead acid to lithium batteries. Do you have any advice to remember during this changeover?
Yeah, obviously the big thing, and I think we've touched on this a little bit, you need to change your charge settings. Your absorb and float charge set points for the sealed lead acid are probably going to be way too high for your lithium batteries. So you'll have to set those, basically the absorb voltage, the float voltage, and the max charge current are the 3 essential settings that your battery manufacturer should be able to advise on. And you'll want to make sure that those are correctly programmed into your charge controller. Beyond that, one other thing you might want to keep in mind, just switching from lead acid to lithium, a big difference is going to be the temperature range that these batteries can handle. Lead acid batteries can handle cold temps, and they don't really freeze or have issues with freezing until it's extremely cold. Lithium batteries are usually not rated for as cold of temps, like below freezing. So if that's an issue or concern, be sure to check the specs for your batteries and account for the temperature change. Um, you're going to see some improvements. Obviously, they'll charge quicker. The lithium batteries, it's higher efficiency and they can handle higher charge rates. So you should see some improvements just in terms of being able to charge quicker. They can obviously handle those deep discharges. So lots of benefits. Those are the main things I would look at, is just making sure your charger is programmed in, and then you have the right settings, and then also just be mindful of being able to monitor that, knowing how deep you're discharging your batteries, however they allow for monitoring. When you switch to lithium, it can be a little difficult to use voltage to tell how charged they are, because they have a really flat voltage curve, and basically lithium batteries always have a similar voltage as they're discharged. So usually you look at if the battery can communicate with your power electronics, it should read state of charge, or otherwise look into finding a battery monitor that's compatible with your LFP batteries that you're getting.
Okay, very good. Again, thanks for that question and answer. Question from Bill, please explain the set point on the TriStar controller.
The set points, I'm going to go back to the specs. I'm not sure if it's something referenced there. I think usually when I talk about charge set points, we're talking about where do you program your charger for your specific battery type. I'm not sure if that's what is referenced here.
Yeah, I'm guessing you're on the right track here, Josh. I think he's talking about absorption set point and float set point, and that would depend on the battery he's using.
Yeah, exactly. So any battery should have recommended charge voltages, whether it's lead acid or lithium, and you're going to have an absorb voltage and a float voltage. The float voltage will be lower, that's essentially the resting charge, and then the absorb is where most of the charge actually happens. The battery manufacturers might use slightly different terms, but there should be two charge voltages. And then we want to make sure that it's charging at the right voltage. And then there's also some other considerations like max charge current and charge time, which we won't get too deep into here, but basically you need to make sure you're not overcharging your batteries with too much current or for too long. Beyond that, the TriStar, you can pick basic profiles, battery profiles with dip switches. I think there's 5 or 6 options for common lead acid batteries, but in most cases you actually do want to get in on a computer or on the meter and program in the specific set points, exactly what your battery manufacturer recommended. So you'd be programming in an absorb charge voltage, a float charge voltage, and then you'd probably be looking to make sure that you're not going to send too much current, too many amps into the batteries that it would potentially damage them.
All right. Thank you for that question, Bill. I see. Let's see, a question from Ron. He says, is there someone I can talk to that can help me with my solar project? And that has grown out of a level of, I guess, above and beyond his knowledge. So I'm guessing, Josh, that would be a good one for you. So you'll be able to see his name and contact info, and vice versa, Ron, if you want to reach out to Unbound Solar, please do. I think that they'll be able to handle your project. All right,
Yep,
let's
happy to help.
see. Question from Joy. Let's see. It has been known that MPPT charge controllers convert the extra voltage from the PV array into usable current. Do we have the math for the current change? What's the best way to answer that question?
Let me try to, that's a great question. I didn't really have a slide prepared for that, but I should have. Let me try to run through an example. So if we have a 12 volt panel that comes in at 18.5 volts and our battery is charging at 14.5 volts. So that's a difference of 4 volts. If we use a PWM controller, that extra power is just lost essentially. So we're losing 25, 30%. If you're using an MPPT, you'd be able to capture that. And the way you'd calculate it is, let's see, you'd look at max power, let's say it's 100 watts divided by the charging voltage, and then times 99% or something like that. Let me see, I could actually pull up my calculator. And so if we think, let's see, it was a 100-watt panel we're using, for example, 100-watt panel times 99% efficiency, it's still 99 watts after the charge efficiency, and we're charging at 14 volts, so 99 watts divided by 14, I think I said 14.5 volts, 6.8 amps. So that's how you'd calculate. You just take your wattage times efficiency, 99%, divided by the charging voltage. Your absorbed voltage is what you'd use here, not your float voltage. So 6.8 amps. Another way you could look at this is 6.8 amps times 14.5 volts is about 99 watts. There's some rounding error there. Hopefully that helps. That's how I would do the math.
Okay, yeah, I think that clears that up. Thanks for that question, Joy. All right, question from another Bill. How much less efficient is a PWM controller versus an MPPT controller?
At least 15 to 20%, and in some cases it's about 25% less efficient. Let's see. So let me actually go back to my calculator. Sorry, I'm switching around a bit here, folks. If we take that same 100-watt panel and take a PWM example, it would only charge at 14.5 volts times 5.94 amps, I think. So on a PWM controller, that 100-watt panel is only 86 watts, and then there'd also be the times 99% efficient. So in this case, that 100-watt panel is only 85 watts going through a PWM controller. This will vary a little bit depending on your voltage and a couple other things, but you can see in this case, your 100-watt panel automatically gets degraded to about an 85-watt panel if you're using it on a PWM. And the reason is that it's coming in at 18.5 volts, but we're only using 14.5, so we're losing 4 volts, and divided by our total, it's about 21. We're losing about 21% of our voltage and about 15% of our power based on that example. So it should be in the range of 15 to 20% more efficient to use an MPPT, potentially a little more in some cases.
Okay, very good. This is a really nice question coming in from Paul. He said that he read on an online blog that it stated that not more than 2 parallel battery strings should be run off of a single controller. He's wondering, is this true? And if so, why?
Yeah, that's a great question. We've also heard that from lead acid battery manufacturers. And by the way, this would apply to lead acid batteries and not lithium ion. Most lead acid battery manufacturers will only recommend 1 or 2 strings in parallel. Some of them will be okay with 3, but usually what they tell us is, max 2 strings in parallel is ideal. Anything beyond that, you need to go, basically you need to use a higher capacity, lower voltage battery, like a 6 volt or a 2 volt eventually. So why is that the case? Why can't we just wire a bunch of batteries in parallel? What happens with lead acid batteries, they have such a high internal resistance, and when you wire a bunch in parallel, you start to create potential current paths where batteries can charge and discharge unevenly. Let's say you have 5 strings of batteries in parallel. You might have some that are getting charged more than others, or some that are getting discharged more than others. Over time, that imbalance is going to grow. Some batteries are basically going to be overcharged. Some are going to be undercharged. And usually a battery will fail either from overcharging or undercharging, and that'll have a cascading effect where it'll basically take out a string and eventually all your other batteries if not caught. So the reason you don't want to connect too many batteries or strings of batteries together if they're lead acid is because it just creates the opportunity for uneven charging or discharging, and that's what's going to damage your lead acid battery. It's not an issue with lithium ion batteries because each one is going to have a built-in battery management system, and that helps regulate the charge and the cell balancing. So if one of them was getting more or less charge, that's not necessarily a big issue with a lithium-ion battery, it has a battery management system that can help regulate that and make sure that each individual battery is okay. So sometimes in lithium installations, you might see like a dozen or more lithium batteries connected together in parallel. That's because each one has a battery management system regulating the voltage and current and the cell balancing and some other things, and so it can handle that. So for lead acid, we recommend 1 or 2 strings in parallel and not any more, unless the battery manufacturer is specifically okay with it. And then for higher power requirements, you'd have to go up to a 6-volt or eventually a 2-volt battery. This is why they make 2-volt batteries that, they're usually 2-volt and over 1,000 amp hours. You can wire 24 of them in series for 48 volts at 1,000 amp hours, for example. That's a way where you can build high capacity banks without having a bunch in parallel. And there are 2-volt batteries, 2-volt lead acid batteries that go up to, I think the biggest we sell is probably like 3,000 amp hours or somewhere around there. So if you did 2 strings at 48 volts, 48 batteries, you could have, 5,000-6,000 amp hours with a lead acid bank that you'd be able to charge. The ideal configuration for lead acid batteries is 1 single string in series. Well, I should say it's ideal in terms of charging efficiently and effectively. There's no parallel paths for current. It all has to go through that string. There are some benefits for parallel strings, like if you have a failure in 1 string, you can unhook that string and potentially still operate on the other at reduced capacity. But really battery manufacturers will usually advise on 3 or often even 2 strings max in parallel if it's a lead acid battery.
Okay, very good. I see a question from Jurgen coming in here. Let's see, this is about 60 cell modules. All right, let's see. He says, you said MPPT controllers are better for 60 cell modules. And he says, for example, I have 2 60 cell modules in parallel with optimum operating voltage at around 29.4 volts when new. He says, I assume they drop the voltage with age. His question is, does an MPPT controller work with this on a 24 volt system?
Yeah, it's a good question, and it's going to depend on a lot of factors. Things like your temperature and the climate. Hot temps will lower your voltage, cold temps will increase your voltage. So that might have an impact. It's also going to depend on your battery type. A flooded lead acid battery at 24 volts is going to charge at like 32 volts. A sealed lead acid battery, well, that probably only charges at maybe 28, 29 volts max. You might be okay there, but it's still kind of cutting it close. If it's a lithium battery, it maybe charges at just under 25 volts or around 25 volts. That would actually be, you might be okay with a lithium battery, but it really depends on these factors like what's the temperature, how much voltage drop is there and is that having an impact? What's the battery type and what does it charge at? In general, I would say that that your 2 panels in parallel at 29 volts is probably not high enough in most cases, but you might be in the right climate and have the right battery type where it could be workable. It's not really something I would recommend. You could charge 12-volt batteries, no problem, with your 2 60 cell panels in parallel. Another thing you could do, assuming your MPPT controller has, a high enough input voltage, is you could wire the 2 in series, and then you would have, you'd have about 58 volts coming in. That would be high enough to charge a 24-volt bank, no problem. So assuming your MPPT is rated for, 100 volts or higher, you could actually rewire those 2 in series and then charge 24 volts like that.
All right, thanks for that. I have a question from Stacy, I see here. What is the threshold low voltage for the MPPT controllers, and can the controller recover from low near zero voltage on its own?
Yeah, that's a good question. I have the TriStar MPPT specs here, and at least for this particular model, it can operate down to 8 volts. So it would not be able to recover from 0 volts. I would honestly say if you have batteries at 0 volts, you probably shouldn't try charging those without, certainly without some inspection and without some testing, because you might have a shorted cell or several shorted cells. Keeping in mind anything below, if it's a 12 volt system, 12 volt battery, anything below about 11 volts resting voltage is totally dead. So if your batteries are resting at below 11 volts, they're completely discharged already. If they're at 0 volts or really anything less than 11, you're basically damaging those batteries, and they need to be charged right away. So I would be really hesitant to try to charge a battery at 0 volts. It might not even be safe to charge. It's possible the voltage will come up and it'll recover, but honestly, at that voltage, it's pretty risky to even mess with without. You'd want to take your multimeter, check if it's a flooded battery. You'd want to actually open up cells, make sure it has enough electrolyte covering the plates, make sure that the cases aren't swelling, there's no damage to the terminals, there's not, if the system's operating, there's not any excess heat coming from the batteries or battery connections. Those would be the things I would want to check. But I think to answer your question, the TriStar would go down to 8 volts, at least in this case.
Okay, very good. I think we'll take one more question because we're past the hour here. Appreciate everyone with us. Let me just, before I get to that, let's see. Somebody's asking for our charging algorithm. I don't know if we can give that out. That's pretty, that's a great question, but I think the engineering, first of all, I don't have it at the tip of my tongue. And I think the engineering team would be pretty upset with me if I gave out that proprietary information. Great question though. Let's see.
Yeah, and I mean, generally, it's going to do a multi-stage bulk, absorb, float, equalize charge, or at least the TriStars are going to be able to do that multi-stage. And then you can program those charge set points to whatever level you want. There is some info in the TriStar manual about the different charge states and kind of how voltage and current changes, but I'm not sure what's being asked for here, if they're asking for like specifics on the charge algorithm or just general info about the charge profile.
Yeah, not exactly sure. So we might have to take that one offline. Let's see. Let's see if we can get to here we go. Last question of the webinar. Can TriStar controllers be installed in the open outside with only rain shelter? Is there an issue of humidity and temperature extremes in sub-Saharan Africa?
Yeah, they're not rated for outdoor installation. Just trying to see if we can find anything on the data sheet. I don't think I included the entire data sheet here, but we would basically recommend putting that in an enclosure where it's protected from the elements and the environments, the TriStar that is. There are small PWM controllers that are rated to be outside. There's the Sun Guard and the Sun Keeper models.
Sunkeeper, yes, I definitely know the Sunkeeper is rated for outdoors, but those are much smaller.
Yeah, I think the Sun Guard is like 4.5 amps. The Sun Keepers are 6 or 12 amps.
Yep.
So those are small PWM controllers for a single panel. Those are used commonly in like the oil and gas industries and some other applications where they need outdoor controllers and they need certain ratings in their small applications. No, the TriStar we would really recommend putting in an enclosure and sealing it from the environments as best as you can. And then if it is a sealed enclosure, you would have to account for the temperature rise that's going to happen. Heat is going to build up if it's in a sealed box. Vented box, it wouldn't be an issue if there's good ventilation, but in a sealed box, there's going to be temperature rise you'd have to account for. And I think I mentioned Morningstar does have a white paper about calculating temperature rise in enclosures.
Okay, very good. So I think that well, we covered as many. There's a lot more questions here, unfortunately, that we're gonna have to take offline. But I think we're gonna have to close things out. Yeah, appreciate you advancing to the thank you slide. I did see a question here about pricing. Actually, pricing is really maintained by our distributors. but just a basic question somebody asked, if a sun saver, if it's lower cost in comparison with the TriStar, the answer is yes, to that question. Otherwise, I do see there's probably about almost a dozen more questions here that unfortunately we can't answer all of them in the time slotted today. So with the thank you slide up here, I'm going to thank you, the audience. I'm also going to thank Josh for all the great presentation and answering of the questions that came in. And we will get back to you by email for those of you that we could not answer here today. So with that, we're going to wrap up the broadcast. We'll see you next time. And have a happy holidays, everybody. Take care.
Thanks, Mark. Thanks, everyone, for listening.